People in our industry have many years of experience in containing hydrocarbon liquids and gases under safe conditions which prevent their release. Therefore, encountering flammable atmospheres is usually a rare occasion. However, at times we must break the containment of pipework and vessels to carry out maintenance and modifications. At these times, great care must be taken to purge and clean the equipment before starting work. As the AGT, you will be asked to check the equipment to ensure that a flammable atmosphere does not exist before work begins. Explosive atmospheres can be caused by flammable gases, mists, or vapors. If there is enough of a particular substance mixed with air, then all that is required is a source of ignition to cause an explosion. The gas-to-air ratio that will cause an explosive atmosphere varies depending on the type of gas, but the testing equipment we use will alert us before the flammable atmosphere reaches a point where an explosion can occur. We learnt earlier about the movement of gases in the atmosphere, and we also know that gas and air must mix in a certain ratio before it has the potential to create an explosive atmosphere. Let's now consider what happens when gas under pressure escapes through a faulty flange or a hole in the pipework. The gas escapes under pressure in a fine jet, usually in a horizontal path away from the release point. But gradually, if it is a light gas, it will start to rise. As the velocity of the gas release reduces, the gas plume will spread out as it moves upwards. The speed of the gas moving through the air will cause turbulence, allowing the gas and air to mix more quickly. This, in turn, can create the gas-to-air ratio required for an explosive mixture. Rising gas and air plumes tend to reach a height where the velocity slows to a point where the gas and air mixture is caught by the wind. This can move potentially explosive atmospheres away from the point of release and is something that you must always bear in mind. On the 1st of June 1974, at the UK Flixborough Works, a 20-inch bypass line ruptured, and a large gas and air cloud formed above the plant before it found an ignition source, and a massive vapor cloud explosion occurred. 28 workers were killed, and a further 36 suffered injuries. A further 53 injuries were reported off-site. The plant was completely destroyed, with distillation columns collapsed and structural steelwork bent and twisted. This example shows how gas plumes can form large flammable clouds, which can be devastating if an ignition source is found. We know that gas and air, when mixed in a certain ratio, can form an explosive atmosphere. If there is too much air, then the gas and air mix will be too lean, as there will not be enough fuel to form an explosive atmosphere. However, if there is a large proportion of gas mixed with too little air, this is considered too rich and again will not form an explosive atmosphere. The first level where an explosive atmosphere may be formed is called the lower explosive limit, or LEL. This is the point when the gas and air ratio are at a level where an explosion could occur. Let's consider methane, one of the most common hydrocarbon gases to be found in our industry. Only a small amount of methane is required in air before it reaches its LEL. 5% volume of methane in air is its LEL. Any ratio of methane from 5% to 15% by volume in air will form an explosive atmosphere, and this is called the explosive envelope. Any ratio above 15% by volume in air is deemed too rich to cause an explosion, and is known as the upper explosive limit, or UEL. As the AGT, it is the LEL which is important to you, as the gas testing equipment will alert you before the LEL is reached, and will warn of the buildup of gas. However, any reading above the UEL should not be ignored. Any turbulence caused by the wind, plant configuration, or the velocity of the gas escape can soon increase the air-to-gas ratio, and dilute the gas and air mix until it moves back to within the explosive envelope. Let's try an exercise to test your understanding of the terms and definitions that you've come across in this section. The diagram on screen shows the UEL and LEL of methane and areas that represent different ratios of methane in air. Select the area that represents the explosive envelope for methane. When you're happy with your answer, select the Submit button. Well done! That's correct. Let's now consider what you will see and hear when you are carrying out gas testing. Most critical parts of the plant, which have the potential to release gas, will be covered by fixed gas detection equipment. Examples of this are gas compression areas, which are covered by fixed gas detectors. These systems normally alarm at 20% of the LEL. In the case of methane, this alarm would sound when 1% of methane by volume in air is detected. Remember, this alarm is the warning that gas is present in the atmosphere and that there could potentially be a problem. Once an alarm has been confirmed on the control room fire and gas panel, you will be asked to investigate to confirm a gas leak or to confirm a fault on the fixed gas detection system. The fixed system will alarm again at 60% LEL, which in methane's case is still only 3% by volume in air. The portable gas detection equipment which you will use will normally be set up with alarm settings between 10 and 20% LEL. For leak detection purposes, in other words not process monitoring, the first alarm level should be set as low as practicable, preferably no higher than 10% LEL. The second alarm level should be no more than 25% LEL. Do not confuse percentage LEL with percentage by volume in air. 20% methane by volume in air is a dangerous level, which could quickly creep into the explosive envelope.